Hi, welcome sa subject natin, Principles of Steel Design. And for today, we will be discussing analysis of tension members. So basically, we are just cascading everything that we have um, talked about from the very beginning, and then we'll try to calculate the overall capacity of our given section according to what we have learned so far. Okay, so as a recall, so we have here the design philosophy for LRFD, and according to LRFD philosophy, our required strength or our loading should be multiplied by a load factor to be able to magnify the loads that are acted on our member, and then it's supposed to be less than or equal to the design strength or the resistance of our section or the capacity of our section. And this value should be multiplied by a resistance factor that is normally less than 1. Okay. And also we also discussed already the load combination for LRFD. And as we have mentioned before, the load combination that produces the worst case response will be used for design. For problems that the given are only dead load and live load, we will just focus on these two load combinations, which is highlighted on this sheet. So for dead load and live load givens, these two will be the only load combination that we can actually check. Okay, and we also discussed the different strength limit state for tension members. So actually there is another one, block shear strength, but for now we will just discuss these two. We're in tension yielding in the cross section. We mentioned that our capacity, since we are using LRFT, we will multiply it by the resistance factor. And we know that the capacity's formula is Fy times Ag, wherein our resistance factor for yielding will be zero point 0.9. That is why we have the value zero point 0.9 Fyag. And it should be greater than or equal with our ultimate load, which is from the load combinations that we have mentioned earlier. And then we have tensile rupture strength, wherein our formula is almost the same, but the value for the FU is different, but can be is available depending on the type of steel material that we have. And AE, where in AE we know that this is the product of our net area and our shear lag factor. So the formula or the capacity for tensile rupture will be 0.75 times the ultimate strength times the effective net area, and that factor or that capacity should also be equals to greater than or equal to our ultimate load. That is again um, calculated based from our load combination. Okay, and as a reminder for our course, we will be using these three type of steels. So we need to be very familiar with the value of Fy and Fu for each cases or for each type of steel. For A36, we have 36 and 58. For A572, grade 50, we have 50 and 65. And for A992, we have 50 and 65 also. For other properties of steel based on a different type of steel or grade, we can refer to this section. So for roll strips, we can refer to table 2-4 of the AASC 14th edition. And for if it is a plate, there should be 2.5, 2-5. Okay, so 2-5 is for the properties of plates. Okay. Next, we also discussed the whole formula for the net area, and if our connection is a bolt connection, we can consider this formula wherein we incorporated or an additional formula, which is to account for the staggered effects or staggered factor for staggered type connection of bolts. So we have a simplification of that formula. Whenever our type of connection will be a parallel or grid type connection, automatically our ND or the number of diagonals for our bolts will be zero, so this will be disregarded if it is a parallel type connection. But if our connection is a staggered type connection, so we will be utilizing this formula, and then we'll just identify the most critical path available on our connection. And then if our connection is a welded connection, it is assumed that AN will be equal to AG. Why? Because no material is being removed, no material is punched, no material is deducted from our section. Therefore, the area to be used on the formula for rupture will be the same as AG. So if we are trying to identify the value of the capacity for rupture, the formula that we have of ppn is equals to 0.75 FU AE. AE will automatically be equals to 0.75 FU, then our shear lag factor times AG. That is for welded connection. Okay. And then lastly, we already discussed how to calculate our shear lag factor. We already discussed the different cases involved and what are the considerations to identify which case um, is governing on our connection. So we have to apply that knowledge also to identify the capacity of our section. All right. So for now, we will be solving an example to demonstrate the use of all of those um, concept that we have already uh, discussed prior to this video. So we have here a 12-meter long W8 by 24 A992 steel is to be used as a tension member. A 20 diameter bolts are employed. If the members is subjected to a service dead load of 350 kilonewton and a service live load of 400 kilonewton, can the member resist these loads? Another question is, does the member meet recommended slenderness limitation? So we have here a wide flange or W-shaped section wherein the flanges are connected in the top and bottom. So we have this type of connection. We have here the spacing of the bolts from the edge and then from each other. So we will be utilizing these values when we calculate the number or the value for our shear lag factor. But for now, we need to identify what are our given for this problem. So um, with this problem, we can easily identify that the length given is 12 meters. So L is equals to 12.0 meters long. Okay. Then we have an A992 steel. A992 steel properties. So we just need to go back to our discussion. Fy will be equals to 50 KSI and Fu will be equals to 65 KSI. Okay, so in metric, we can easily convert KSI to megapascal by multiplying KSI value times 1000 to make it in PSI and then divide it by 145 and the answer will be in megapascal. So for this case, 50 KSI, okay, so 50 KSI times 1000 all over 145, that is 344.82. So we can assume that this is equals to 345 megapascal. And for the 65 PSI, 65,000 divided by 145, that is 448.27. So assume 450 megapascal. Okay, so just to have a more whole number for our values of Fy and Fu. And then what else? The next given is we have the diameter of our ball. Okay, when that is given, dB is given 20 mm, we can now easily calculate the value for our effective hole diameter. Okay. And since the diameter of bolt is given, we have the formula dE is equals to dB plus 4 mm. That will be 20 mm plus 4 mm. Okay. Then dE will be equals to 24 mm. All right. Next, we have the given loading. So it is stated here, this are service dead load. And service live load. Take note, once na service loads ang pinag-uusapan natin, it means that the loads are still unfactored. Meaning wala siyang magnifier, wala siyang load factor. So if our design philosophy that we will employ is LRFD, we need to use our load combination to arrive with the most um, critical value of our force. Okay, so using the our load combination for LRFD, we have PU is equals to 1.4 PD. Okay, and PU is equals to 1.2 PD plus 1.6 PL. So what is PD and PL? So PD is 350 kilonewton and PL is 400 kilonewton. So let's substitute. Okay, so we have here 1.4 times 350 kilonewton. Then here 1.2 times 350 kilonewton plus 1.6 times 400 kilonewton. So this will be equal to 1.4 times 350, that is 490 kilonewton. Then we have 1.2 times 350 plus 1.6 times 400. That is our uh, next value. Okay, 1060 kilonewton. So between the two values of two load combinations, we need to select the most critical, which is the largest or the maximum value. So for here, this is our governing load. So we now identified the ultimate load that we need to satisfy on our um, LRFD requirement, which is our capacity should be greater than or equal to PU. Next is we need to identify now our value for VPN, our capacity or resistance, and that will be based from our limit states. Okay, so for our limit states, okay, let me write here. Okay, um, we have two limit state so far. So we have the first one, which is gross section yielding. Okay, its requirement is VPN should be equal to zero point 0.9 FYAG. Okay, so we can easily identify that. And then for our next limit state, we have net section fracture. We have the formula VPN is equals to 0.75 FUAE. Okay, so before we can solve that, we need to identify the properties of our section, and our given section is a W8 by 24 section. So we will be referring to our W-shaped table to identify the needed property for our given section. So W8 by 24 properties. So we need to identify what properties are essential for us. Of course, we need the gross area, okay? Because we will be using it in the formula for cross section. Next is for our net area. Inside this effective net area equation, we need to get the thickness of our flange, okay? Because we need to deduct the number of holes, so we will be using, or we will be needing the value of the thickness of the flange, okay? Next is for, since in the question it is also stated that we need to meet the recommended slenderness limitation, and according to our discussion, slenderness limit can be satisfied using the formula L over R less than or equal to 300. So um, we need the value of the radius of gyration of the section. So we have to indicate also Ry and Rx, or Rx and Ry, then use whichever is minimum. And then later, although it cannot be um, proven right now that we need it, but we will be needing it once we go on the calculation of the value of the shear lag factor. We will be using um, the width of the flange and also the value for the depth. Okay, so let us go to the W shapes of the construction table, and then we try to look for W8 by 24. Okay, W8 by 24 is somewhere here. Okay, so W8 by 24 is this one. Okay, and we need its area, that is 7.08, the depth. Okay, so 7.08. Okay, so we have 7.08 inches squared. Then next is the thickness of our flange. Thickness of the flange is this one, zero point 0.4. Okay, zero point 0.4 inch. Rx and Ry we need also. So going back, Rx and Ry is here at the other side. So this is our 24. Rx is 3.42. Ry is 1.61. 3.42, 1.61. 3.42, 1.61 inch. Okay. Then our width of the flange is given as width of flange. We have 6.5 inches, and the depth is 7.93. 6.5 and 7.93. Okay, 6.5 inches and 7.93. Okay, so before we can continue with our calculation, we need to convert our values into its equivalent metric values. So we multiply this area by 25 mm per inch, and then we square it. And then for the others, we just multiply by 25 mm per inch. Okay, 25 mm per inch, 25 mm per inch, then 25 mm per inch. Right? So we have 7.08 times 25 squared, we have 4425 mm squared. Next, 0.4 times 25, that is 10 mm. Next, 3.42 times 25, we have 85.5 mm. Next, 1.61 times 25, we have 40.25 mm. 6.5 times 25, we have 162.5 mm. And 7.93 times 25, we have 198.25 mm. Okay, so now we have the properties of the W824 that we need for our calculation. We can now start with our capacity. So for gross section yielding, that will be 0.9. Fy we identified to be 345, okay, megapascal. So 345 megapascal is also equal to Newton per mm squared. So multiplied by our area, which is 4425 mm squared. This will be cancelled out. So our VPN due to yielding will be zero point 0.9 times 345 times 4425. That is equals to 1,373,962.5 divided by 1,000. We will have 1373.96 kilo Newton. That is our value for yielding. Okay. So next, we need to calculate the next net section fracture. Okay, so let us just this leave that for a moment. For the net section fracture, we have AE, that is the effective net area. Effective net area formula is AE, and we know that AE is equals to U times AN, and AN is our net area. So net area will be equals to AN. So to identify our net area, that will be AG minus the number of bolts that we will deduct times the effective hole diameter times our thickness of the flange. Okay, so there will be no staggered factor because our connection is not a bolt type, a parallel type connection. So we will just use this equation. Then going back here, the other side, we can see that our connection, when we try to look at the top view of our connection, um, we can say that our top view is like this one. We have four bolts at top, okay, on each side, and this is our loading. So if we want to identify which bolt will rupture first when tension rupture happens, we can imagine that we are facing the brake line, and then we flash or we use a flashlight, and then whichever are the bolts that hit by the light, that is our assumed location of our fracture. And as we can see, it it passes through two bolts on one flange. Since our flanges have bolts on the upper and the lower side, it will be multiplied by two. So in total, we have four number of bolts. So using that idea, our gross area will be 4425 minus four pieces of bolts times the effective hole diameter of 24 mm times the thickness of flange, which is 10 mm. We have our net area, which is 4425 minus 4 times 24 times 10. That is equal to 3,465 mm squared. Okay. Next, we need to identify our shear lag factor U. Okay, shear lag factor. Okay, for our shear lag factor, we need to go back to table D3-1 and look for the cases that will satisfy. And as mentioned from the previous lecture, for case one, we need all elements to be connected by bolts. But in our condition, it's only the flange. Therefore, it is understood that our case one will not be justified, but we will accept case number two. Okay, so our cases for our shear lag factor will be as follows. So cases will be case two, and also what else? For case three and four, we have for welds. For five and six, we have HSS. For WMS or HP shape, that is for case seven, which is our case. Number eight is for angles, so we need to omit eight. So we accept case number seven. And for case number seven, there's it has two subcases for flanges and for web. For our case, we will use web. And since we satisfy that we have three or more fasteners per line, so we justify this requirement. So we need to check whether our BF will be greater than or less than two-thirds of T, whichever is the value. Okay, so let us calculate that value. Okay, so case 7 also. Okay, so for case 7, we need to justify or to check BF and two-thirds of D. So for BF, we have 162.5. Then for D, we have 198.25. Okay, so 162.5 for BF, 162.5. Then we have two-thirds of 198.25. So two-thirds of 198.25, we have 132.17. So comparing these two values, BF is greater than two-thirds of T. Therefore, U7 for K7 is 0.9. Okay. Next, we identified the value of U2. U2 is equals to 1 minus bar X con all over L con. Okay. And according to our discussion previously, when our section is a wide flange connected in the flange, that is a special case of connection eccentricity. So we need to go back to this discussion that for W sections connected by the flanges, we need to convert the wide flange section to an equivalent WT section to get the value of bar Y, or the distance from the connected face going to the centroid of our section. So we need to get the WT counterpart of W shape section. Okay, so for our case, our section again is a W8 by 24. Okay, so W8 by 24. So we need to get WT 4 by 12. Okay, and identify the value of our centroid. So this is our section. This is the centroid. This is the connected face. So to get the value of x cone, we need this value, x cone, which is also equivalent to the value of bar y. Okay, so going to WT shape table, this is our WT shape table. We need to find WT 4 by 12. So we have here WT 4 by 12. This is it. Then we need to get bar y. Bar y is here, bar y. So we need to go back to go here. So that is 0.695. Okay, so 0.695 inch. So x cone is equals to 0.695 inch. And since our unit is in mm, we need to multiply it by 25 mm per inch. So that is 0.695 times 25. We have 17.375 mm. Okay. For L cone, we need to measure the out-to-out distance of the bolts. So this is the end of the last bolt at one end, and this is the last bolt from the other end. So we have this as our L-con, okay, which is equal to the sum of these spaces, 75 times plus 75 plus 75, we have 225 mm, okay? So 225 mm is our L-con, 225 mm. So we can calculate now U2, 1 minus 17.375 mm all over 225 mm. Cancel out the units. We have U2 is equals to 1 minus 17.375 all over 225. That is equivalent to 0.923. And we need to read the citation stated on case number 7 of D3-1. It says, if U is calculated as per case 2, the larger value is permitted to be used. So we need to select whichever is larger between U7's value and U2's value. And comparing this value, we have U7 as 0.9, U2 is 0.9923. Therefore, this value governs. Okay. Next, so after identifying our shear lag factor, we can now continue with the calculation of our capacity now, because we have the required value. So 0.75, then FU is 65. No, we have converted it to MPa, that is 450 Newton per mm squared. We have our U factor 0.923 and our net area of 3465. This is also in mm squared. Okay, so VPN is equals to 0.75 times 450 times 0.923 times 3465. That is 1,079,390. divided by 1,000, we have 1,079.39 kilonewton as our capacity according to rupture. Okay, so what now? Since we identified already the capacity based from the two strength limit state that we need to compare the value of this one and also this one. So for design, we need to uh, identify whichever is the most critical. And for this case, since the capacity of the section is these values, the smaller value should govern. Okay, because when we select this one, there will be a time, or maybe we concluded that this will be the value, but when the actual structure is being loaded in the actual condition, you will see that when it reaches this value, it will start to rupture. So we don't want that to happen. So what we do is we select the smallest between the two and then select whichever is critical. Okay, so this value will govern, and this will be the one compared with our PU. Okay, so our LRFD consideration is our capacity should be greater than or equal to our PU. So 1079.39 kilonewton should be greater than or equal with our calculated PU, which is 1060 kilonewton. Okay, so 1060 kilonewton, since that um, condition is satisfied, we say that therefore this is okay. Section is adequate for our limit states. Okay, so it means our section can carry the given loading and can satisfy the both yielding and ruptures limit state. Okay, that is the answer for the first question. Next, can the member meet recommended slenderness limitation? Okay, for slenderness limitation, we need to satisfy L over R should be less than 300. L over R should be less than or equal to 300. We have a length of 12 meters, so we convert it to mm. We have 12,000 mm. And for radius of gyration, we select the minimum based from the value that we gathered, Rx and Ry. So the least value is 40.25. So we use that value, 40.25 mm, cancel out the unit. 12,000 divided by 40.25, we have 298.137, which is actually less than 300. Therefore, okay, it means section meets slenderness criteria. Okay, so if this is the case, um, we will say that the section is adequate for all the checks that we need to satisfy for tension, tension strength limitations. Okay. Okay. So that's it. That's how you calculate or analyze a given section based from the given loading and the given constraint of the section. Okay. Okay. So this ends our lecture. If you have questions or would like to clarify something, don't hesitate to message me. And I'll see you guys again next session. Thank you.